the current direction this way, right side. Your second finger is right side, and uniform magnetic field into the page. Into the page means towards the screen, right? So forefinger is towards the screen. Then second finger is right side. Then your force is where? Force is where?
Upward.
Upwards. So if it is upwards, then the answer is a force towards the top of the page, right?
Yes.
Okay. Then for the other part, this one QR, right?
Yes, sir.
Again, we are using the Fleming's left-hand rule. If your second finger is now down and magnetic field is still towards the screen, right? Then your thumb is
Yes, sir.
where? Where is your thumb showing? Are you checking?
Yes, sir.
Where it is? The direction of thumb. Your second finger is working downwards, right?
Yes, sir.
And your first finger is towards the screen. Then thumb is
Thumb is to the right.
to the right. Okay, good. Then your answer will be
Right.
towards the right of the. So last one. Battery in the circuit in figure 2.1 is reversed. State and explain the effect of this on PQ and QR. What will be the effect?
Current and force will be decreased or reversed.
Okay, here you wrote current will, all the forces will be reversed.
It should be with current with.
With.
Yes.
Current with. Okay, then it is fine. Can you read?
The
See.
resistor adjusted and the current decreases. Suggest one effect of that of decreasing the current. The force or current might decrease.
They already told you about the current. Then you only mention about the force.
Oh.
The force on the wire will be less, okay, yes, or decrease, not the current. Current is already mentioned in the question. So the worksheet is done.
Yes, sir.
We are going to do now topic 23. Electromagnetic induction.
last class we did only did Lenz law. We didn't start Lenz law.
Which one?
Lenz law.
Okay. You wrote the heading of Lenz's law, right?
Yes, only the heading.
Okay, very good. That day the network was doing problem, right? Again and again you are
Yes,
disconnecting.
yes.
Otherwise we could go forward a little bit. Before going to Lenz's law, we are going to right hand grip rule, huh? Right hand grip rule. Right hand grip rule already you know what is for straight wire, right?
Yes,
Straight wire or straight conductor which is carrying the current, and around it there is magnetic field lines, isn't it? So now we are going to have the idea in different way. If it is not straight wire, it's a coil, then what will happen? That is also Fleming's right hand rule, but we are learning it in different way. It's clear?
yes, sir.
And you are supposed to learn it in topic 17. There is magnetism and electromagnetism. We have the idea of magnetism over there and electromagnetism over there. If current passes through a coil or solenoid, coil is also called solenoid, right?
Yes, sir.
So if current passes through a solenoid, then we get that solenoid magnetized, right? And it's behaving like a magnet. If you are bringing any magnetic material closer to it, then it will attract. That that one is called electromagnet, isn't it?
Yes, sir.
If you stop the electricity, then there is no magnet in the solenoid. Okay, that's why it is temporary magnet.
Yes, sir.
It is temporary magnet. And if you are giving iron in the core of the solenoid, then the electromagnet becomes stronger.
Yes, sir.
I think you got this idea in topic 17. Did you get? Can you recall? Now you should use your right hand to understand it. Okay. Are you ready with your right hand?
Yes, sir.
Okay, very good. Now you take this diagram. Are you seeing the diagram?
Yes, sir.
What you are seeing?
I write and give you.
Okay.
Short,
So you write it the way I wrote. Yeah. Right hand grip rule for solenoid.
the heading.
Hmm. Are you done? Then you
Yes, sir.
draw this diagram. Look, other fingers are showing the direction of current,
Yes, sir.
and the thumb is showing you direction of north pole. Is it clear?
Yes, sir.
Exactly this way you draw. Now it's shown here. Are you drawing?
No, sir. You can see it.
You can't see it.
No, sir.
You can't see. Are you done?
Yes, sir.
Okay. Now look at the diagram 23.4. When we are bringing one bar magnet closer to the coil, what happens? We are getting induced EMF, right?
Yes, sir.
If you are getting induced EMF, then you will get induced current also, isn't it?
Yes, sir.
And because of this current, there will be right hand grip rule for solenoid, isn't it? Yeah, look at this diagram here. The way the current is going, here the current is going, this direction of current is making the solenoid or the coil magnetized, right?
Yes, sir.
And it will be magnetized in a way that our left side will be north pole, isn't it? Just now
Yes,
you
sir.
just now you understood it from the diagram. Your left side will be north pole and right side will be south pole, isn't it?
Yes, sir.
So if here we get south pole, then this south pole will be repelled by this induced south pole, right? We have here in the magnet south pole, and because of induced EMF and induced current, we got another south pole here. So they will repel each other, isn't it?
Yes, sir.
So this repulsion will not allow this magnet to move further, isn't it?
Yes, sir.
So this one is our observation here, and here we have some correction, little bit correction. This side should be positive and this side should be negative, according to conventional current flow. Okay, is it clear?
Yes, sir.
because we got the current direction. That way, this left side should be positive and right side should be negative. Now you draw this diagram, huh? Draw this
Yes,
diagram
sir.
and draw it, and then what I am writing, write that, huh? As the magnet is moved towards the coil, there is induced EMF. Excuse me, I have got cold.
Yes, sir.
Running nose. Okay, now as there is induced current, uh, therefore, or you write so there will be south pole created at the right side of the solenoid, or you can say coil, according to right hand grip rule, right?
Yes, sir.
And grip rule. Hence, the magnet will not be allowed to move further due to repulsion. Is it clear? This statement is clear to you?
Yes, sir.
Now, if you are done with writing and drawing, I will go to another step.
No, sir. I must finish writing.
You are writing or you are done?
I'm writing.
Okay, right. When is your next class?
Next class on Wednesday.
No, today you have another class after me.
Yes.
When?
From 7.
Okay. Are you done?
Yes, sir. Done writing.
Are you done?
Yes, sir. Done writing.
You are writing or you are done?
Done. Yes.
Okay. Okay. Very good. I am only hearing you are writing, writing, writing. Okay. Now, this diagram, look, what we are having here, just opposite, huh?
Yes, sir.
Opposite direction current. Why? The bar magnet is moving out of the coil. Bar magnet is taking away from the coil. What will happen? Again, we will have induced EMF, induced current in the opposite direction. And that's why, according to right hand grip rule, we will have the opposite pole. At the end of the solenoid, we will have here right side will get north pole and left side will get south pole. Is it clear?
Yes, sir.
And what this will not allow now, look, if it is north pole created and here it is south pole, already we have.
Yes, sir.
So what will happen? North pole will attract now south pole. So it will attract, that means it will not allow the magnet to move far away. It will attract, right? It will pull it
Yes, sir.
towards it. It will not allow it to move far away. Is it clear?
Yes, sir.
So one is opposite to another one. Previously it was not allowing to go forward. Now it's not allowing to go far away. It's clear now.
Yes, sir.
So you draw this diagram with this correct symbol of the current, then write what I am writing. Here the magnet is taken away from the coil. So there is induced EMF current in opposite direction which creates an pole at right side of the coil, hence the magnet is not allowed to move far away. So you got here writing. Have you understood the writing?
Yes, sir.
So without explanation, you will not understand it, right? As I explained, you understood it, isn't it?
Yes, sir.
Now, if you are done with
Sir,
writing,
I did not finish reading. No, sir.
okay, okay, finish writing.
Yes, sir. Finish writing.
Now, if you write the Lenz's law, you'll understand also. You wrote here Lenz's law, right?
Yes.
Can you read the law now?
The direction of the induced EMF and hence the induced current is a closed circuit is always such as to oppose the change in the magnetic flux producing.
So magnetic flux means flux.
Yes.
Flux means density of the magnetic field lines. Did you write it?
Yes, sir.
Flux means magnetic field lines density. So here the statement is saying the induced current, direction of the induced current is always such as to oppose the change in the magnetic flux producing. So we are getting the induced current due to the magnet's movement, isn't it?
Yes, sir.
Now that induced current is producing one electromagnet in the solenoid, which is opposing the movement of the magnet, isn't it?
Yes, sir.
That is saying in the statement. Now you understood it.
Yes.
So if it is not there, the diagram and the discussion, you wouldn't be able to understand it. That's why I did not say you to write it first. Now you will understand it, isn't it?
Yes, sir.
Okay. So you learn it. This law you learn. Memorize this law. Now, related to this law, there is another thing left. You see this diagram. Here we have no deflection of the galvanometer. Why? Because there is no induced EMF or induced current.
Yes, sir.
Why there is no induced EMF or current? Because the magnet is not moving. As the magnet is not moving, the magnetic field lines are not cut by the coil. There is no change in magnetic field. Is it clear?
Yes, sir.
So you draw this diagram and the note I am writing here, you write that. We don't get any deflection in the meter as there is no induced EMF or current since the magnetic magnet is stationary. Magnetic fields are is it clear now? What I wrote, is it clear to you?
Yes.
Are you done with writing?
Yes, sir.
So that's all for today, huh?
Yes, sir.
And in next class we will finish it, huh?
Yes, sir.
And I will give the worksheet on topic 23. We will try it, huh?
Yes, sir.
Thank you so much.
Allah Hafiz.
Allah Hafiz.